Hello everyone, my name is Mandy Bowman and I'm a second year master's student in the Computational Science program at San Diego State University. And today I will be presenting my research on the quantum Lanczos algorithm using real-time evolution. So I first want to start by giving some motivation for this research and why we want to use quantum computers. Quantum computers harness the properties of quantum physics such as superposition, entanglement, and interference. And these computers could theoretically provide a significant speed up over classical computers. There are several applications in quantum computing in cryptography, optimization, chemistry, and nuclear physics, which is where my research falls into. And a common task in nuclear physics is to solve the Schrodinger's equation, which is essentially just an eigenvalue problem. Several algorithms have been developed to complete this task, including the one I'll be talking about today, quantum Lanczos or Q-Lanczos. The Q-Lanczos algorithm is based on the well-known classical Lanczos algorithm. The Lanczos algorithm is a method of solving for the extremal eigenpairs of large matrices. So in nuclear physics, one can have Hamiltonians with millions or even billions of dimensions. And this algorithm allows us to find the extremal eigenvalues, or what we call nuclear physics, the ground state and excited states of nuclei, in only tens of iterations. It works by applying the Hamiltonian to some pivot vector repeatedly. And every new vector, which is called a Lanczos vector, is forced to be orthogonal with every previous vector. This creates an orthonormal basis, which is called the Krylov subspace. And in this basis, the Hamiltonian is tridiagonal, and we do not have to carry out the full transformation. So we're able to get these eigenvalues in only tens of iterations. So the Q-Lanczos algorithm, which was developed in 2020, it uses the same idea of repeatedly applying an operator to an initial vector. However, instead of using the Hamiltonian, we use the imaginary time evolution operator. And on a quantum computer, one needs to have unitary operators. So for every few iterations, you have to do a unitary update, since the imaginary time evolution operator is not unitary. So in my research, we proposed using a real-time evolution operator because it is unitary and therefore would be easier to implement on a quantum computer. So in this figure, you can see a comparison between the imaginary and real-time evolution, which was applied to an isotope neon-20 to find the ground state. So we can see that the imaginary time does converge in fewer iterations. However, the real-time evolution still converges in a reasonable amount of steps. But on quantum computers, more time means more noise. So to reduce the number of time steps required for using this real-time evolution operator, we introduced the multiple reference state generalization. By using multiple reference states, we can achieve convergence faster. The algorithm was implemented to find the ground state of neon-20 using 1, 2, and 3 reference states. And in this figure, we can see that by using 2 reference states, the algorithm converged after 6 steps. And after using 3 reference states, it was able to converge using only 5 time steps. I also implemented this algorithm to find the ground state energy of 2 other isotopes, sodium-22 and sodium-29. So in the table, I've compared the results for using imaginary time against the results for using real time with multiple reference states. So we can see for all 3 of these isotopes that we were able to achieve convergence in the same time steps or even less time steps than with the imaginary time evolution.